Lect22. If you haven't signed the data agreement, please make sure you sign it before the end of class. This is for the people working on the healthcare project. How many of you have looked at the traveling salesman problem before? Okay. How many of you have not? Those should be complimentary sets. Interesting. Okay. So traveling.
I think about as many people vote in those as like vote in the U.S. election. You know.
I know, but some people vote multiple times, just like the U.S. elections. All right. For those of you who haven't seen this before, how do you abbreviate the traveling salesman problem?
Teaspoon.
Teaspoon, TSP. But haven't you said you've seen it before?
Yeah.
And we have people following elections just as directions just as well as they do in the U.S. elections. As an aside, when I was a freshman at college, I probably shouldn't be saying this on TV, I may have misvoted in the presidential election. The Massachusetts absentee ballot instructions stated, vote while alone, but in the witness's presence. Yes.
For real?
For real. Yes.
Yeah,
So
did it still say that?
No, they corrected it by the time I was a first year graduate
Mine said
student.
vote while alone. I don't know.
Yeah, mine was while alone, but in the
Very
witness's
carefully
presence.
not to-
Alright. The traveling salesman problem can be used to solve a variety of things. The classical formulation is you have a bunch of cities. These are cities. My artwork is beautiful for something like this. And you have paths connecting some cities to each other. And you may not have every city connected to every city. And what you want to do is you want to choose a path that travels through all the cities in the least amount of something. What do you think the least amount should be?
Time.
One possibility is time. What's another possibility?
Distance travel.
Distance traveled. What's another possibility?
Edges travel.
Edges traveled should be the same because hopefully you never revisit a city. Now, in a network like this, it may not be possible to do it without revisiting the city. The way this is drawn, I think you have to revisit a city. Yes. So, you could do time, you could do distance, you could also do cost. Maybe different legs cost different amounts. If you want to make things easy, you often assume it's a complete graph. And so, I can start drawing in all the different edges, dot, 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 complete graph. So what's the advantage if we assume it's a complete graph? And this one over here is not complete.
We know there is a Hamiltonian cycle.
Okay, so one thing is you have some graph theoretic
We know
results.
that there exists the path we're looking for, at least one.
So there will be a path. Now there's always going to be a path that will go through all the cities, but it might have to go through some cities multiple times. If we assume, I'm sorry?
Yeah.
If we assume that it's a complete graph, there will be a path of minimal length. There may be several paths of minimal length, but we know that at least one such path will exist. We also know that at any moment in time, every city is accessible. So it makes the problem a little bit easier in that sense, in that at every moment in time, any choice is valid, if you haven't visited. So how many possible paths are there? So how many paths do we get? Why n minus 1?
Because we're picking one city, arbitrarily starting city, and then reorder.
So does it matter which city is the starting city?
It does, it's not factorial.
So if it does, if the starting city matters, it's n factorial. So does it matter where we end and where we start? If we had a closed loop, if we have to return to where we started, it wouldn't matter where we start. But we don't have to return to our starting city. Yes?
I just have a question. Don't paths include like just paths of like length 3 on that graph or 2 any path? Like, are you considering a path like going through every node?
Yes. I want to travel through every node. I'm trying not to introduce all the graph theoretic notation in terms of, am I doing a circuit, am I doing a path, whatnot. I just want to visit each city once and only once. Visit each city once and only once. And since we don't have to return to where we started, I think it's n factorial. Now, Stirling's formula tells us n factorial is approximately n to the n, e to the minus n, square root of 2 pi n. If anybody's interested in either proving this or seeing ways to get good approximations to this, let me know.
Is that the probability?
We will be doing this in probability. There's a lot of great ways. If you liked the problem where we added the numbers from 1 to n and we did this kind of reinforcement, you can do a very similar thing here to estimate n factorial. This is growing enormously fast. If you want, look at this as n divided by e to the nth power, square root of 2 pi n. So if I then wrote this as an exponential, this would be e to the n log of n over e, square root of 2 pi n. So this is going faster than exponential. What this means is brute force is not the way to go. Okay, for reasonable sizes of n, it's already going to be too much. So if you wanted to even just visit the capitals of the continental United States, because we really don't care about Alaska and Hawaii. Maybe Alaska we're willing to consider, but Hawaii is definitely out. That's already going to be an enormous number. To get a sense of this, I urge you to go home and actually put in your numbers of the size, 49 or 50, and just see how large this is, and how impractical brute force is going to be at this stage. Okay. Anybody have any ideas how we might solve this? Yes.
Okay, spanning tree is augmented.
Okay, but this is not a class with spanning trees.
Okay.
What have we been doing in this class? Linear programming. So the question is, can we solve this with linear programming, right? Can we write down something? If you want, applications of this, one of the applications that I like is building circuits. In terms of when you actually have machines that are burning things down, you want to minimize the path that it's traveling, because the longer it's traveling, the more time you're spending not doing what you want to do. So how do we do this with linear programming? Solve via linear programming. So we need to have decision variables. Okay? I actually find it's convenient to introduce 2 extra cities, and there may be a typo in the book. The reason, right, so I'm going to introduce a start city, and I'll introduce an end city, and I'm going to assume that when we hit the end city, we travel back to the start city. By doing this, we now assume that every city is entered once and left once. If we don't do this, you have 2 cities that are special. How far apart should the start and end city be?
0.
So one possibility is to make them 0, right?
Or 1.
Or 1, or 2016. Does it really matter how far apart they are? If we always force one of our constraints to be we travel from the end city to the start city, it doesn't matter what that distance is. Given that, let's make the distance 0. We have an experimental transporter that is connected from start city to end city. And so there'll be no cost in terms of traveling from start to end. Okay. Now we need to choose a bunch of intermediate cities. So maybe we go here, and then here, and then here, and then here, here. So what do we want to label these city numbers?
1 to n?
Yeah, I'm not really thrilled with how I labeled them in the book. Let's label them 1 through n. So 1, 2, 3, n minus 1, n. And I'll put some ... dots here. So we need some decision variables. X, T, I, J will be 1 if at time t leave I for j and 0 otherwise. Approximately how many time periods will we have? Within like 1 or 2, about how many time periods are we going to have? Yeah, it should be like n. We have to decide how do we want to do things. This we'll probably call city 0, and we'll call this maybe city n plus 1. And so at time 0, are we leaving start for city 1? I think so. And then at time n plus 1, we're leaving the end, or is it at time n? So time 0 gets us to city 1, time 1 gets us to city 2, so I think time n minus 1 gets us to city n, so time n would get us, I think, from end to start. I always have to play this little quick calculation to figure out what's the final value. So time goes from 0, 1, all the way up to n. Yes?
Is the distance from S to 1 and from N to E also 0? So it doesn't matter which of the real cities you pick as your first one and last one?
Excellent. Yes. So in fact, we would need the distance from S to any city.
Okay.
And we would also need the distance from any city to end.
Okay.
So now we need to start putting in some constraints. So dij is a parameter. It's going to be the distance from I to j. So these are parameters. These are not constraints. But we will use them to build our constraints. Okay. Now, as was remarked, we need to initialize a bunch of these. So for all j, d0j equals 0. For all I, di n plus 1 equals 0. So no cost to go from start or to end. And again, we don't have to add a start and an end. I just think it's convenient to have them there. Now, in some sense, all the cities are equivalent. And then we just put some special constraints on the parameters. I think it's just a nice way to code it. This is very similar to how we did the Sudokus. Should we have our Sudokus 1, 2, 3, 4, 5? No, how should we do the numbers in our Sudoku? 1, 10, 100, 1,000. Right? Try doing that on an airplane and see what the person next to you thinks. Yes?
Wait, so that's so that it doesn't matter whether we start at the start or the end?
No, this is so that it doesn't matter which city we go to first.
Okay.
So when we're doing the traveling salesman problem, there's a couple of ways of doing it. One way is that you specify where you start. Another is you can start anywhere in the network, and then you want to have the shortest path from that starting point. It's a little bit easier if we know where we start. It's also a little bit easier if we know where we want to end. You think of it as you're doing a road trip, which some of you may do at some point in your life. You probably know where you're starting, and you probably know your destination. Not always, but usually. And you might have a bunch of things you might want to see along your way. You might be just trying to decide what's the best path to take to go through all these different places. Okay, are there any other parameters we need? So we've got the distance between all the cities. We've specified our times. We've specified our binary variables. Is there anything else we need?
You only want to visit each city once, right?
So we only want to visit each city once. So that's not a parameter, but that's now a constraint. So now let's start putting in constraints. So visit each exactly once. So what would it mean? So for every city I, what would it mean to visit it once? Yes. Well, maybe do we want to do it with I, or do we want to do it with J? I think it makes more sense to do it with J. For every J,
the summation of all t,
Good. The summation of all t,
summation of all I,
summation of all I,
x t I j,
yep.
equals 1.
Good. So you specify a city J. I sum over all possible cities that could be traveling to it. And I sum over all possible times. And this equals 1. So what that means is I have to visit J once and I can't visit it twice. We actually know a bunch of these decision variables are 0. Can anybody give me an xtij, which is definitely 0?
X 0, n plus 1, 0.
Okay, so we have a bunch of things where we know we're not going to immediately go from the start to the end.
Well, I was going to say we're not going to go from the end to the start the first time. Also.
Right.
That's where I equals j.
Yeah, whenever I equals j, we know those are going to be 0. So if you want, we can even explicitly put those in the model to help it, to say, hey, look, this variable has to be 0. If not, it's going to come into play. Or do we have to worry about it? Or do we have to put it in? Is that a possibility? Let's say I visit myself. I'm not quite sure exactly what that means. I could be entering and leaving. Would that count?
Why would we want to do that?
We don't. We want to have a connected path. So what I'm saying is, do we have to add a constraint such that you never visit yourself? Or is there another constraint we have that will take care of that? So I'll do one other constraint first. So first, we visit each city exactly once. Yes?
If we say that by time and we have to have made it to the end, you would never like revisit yourself. You wouldn't be able to like go back into the space.
Well, what I'm saying is, does this count as this city has one visitor and also has one leaving? I both arrived and left, and I could have something disconnected. So maybe I have a path like this. And here's my start, here's my end. Maybe I have something like this. We don't want to allow this. So we need a constraint that will stop this. One constraint that would stop this is to just require, whenever I equals j, that equals 0. And that might actually help the program because it's going to force those variables to be 0. It's going to cut down on some of the freedoms. Yes?
Couldn't you just get a 2-cycle then if you said that?
If we did, yes, we would have, which is not good. Here, there's only one transporter, it's a prototype. It only works between start and end. This transporter is not working in other places. There should be a constraint that's lurking here that would prevent this from happening. What constraint do you want lurking?
Yeah, I don't understand why we don't want that.
Well, if I'm trying to do a path, how do I jump from...
like that's the same graph.
This is the same graph, yes. You should not have it disconnected where, I travel and then all of a sudden I somehow go through the air and end up in 0 time at 0 cost in another place. We don't want to allow this. So one thing is, it's not necessarily bad to say, also, for all t, x, t, I equals 0. That will prevent something like this. It's not a bad constraint to just put in. I think will help the runtime. There is another constraint that we will put in that will eventually, I think, kill this issue. What's going on here that we would want to codify into a constraint? Yes? We want a complete graph. So what does a complete graph mean? So we want a connected graph. So this is not going to be connected. So what we want is that if you enter a city, you leave a city, and if you enter a city at the very next stage, that's where you have to leave from. So if at time t, I enter city j, at time t plus 1, I must leave city j. If we put in a constraint like that, that will eliminate this possibility. Which is a reasonable constraint to have. If you've entered the city, that's got to be the next city you leave from. All right? So it's worth just spending a little bit of time thinking about what kind of constraints you might want to put in. Yes.
So what's a counterexample where that condition is not satisfied by this segment? Yeah.
Oh no, as soon as I put this line up, that prevents something like this.
Sure, okay, so.
Right. So one possibility is if I put this in, I don't have to worry about any of that. The problem is, as soon as I put that in, I've added some additional constraints, which is not necessarily bad. A better way of doing it, though, is rather than adding this constraint, what should you do rather than adding this constraint? Remove some variables. Right? We never need to introduce those variables. Could instead remove variables. Then this comes down to issues which I don't know. In terms of actual implementation on the software, which is better? To have these variables so that you can freely move things, but just set them all to be 0, or to just do your programming in such a way that you never allow I to equal j when you're listing your constraints and your variables. So depending on the system you're using, sometimes it's easier to program one rather than the other. I think it's much easier to just have all x, I, t, j as variables, and then just add these constraints. It's a very easy line to add. But it might slow down the runtime by putting in all these variables, which you then initialize immediately to 0. But maybe the system is smart enough to know that if you've initialized it to 0, don't bother trying to change them. If they have to equal 0, they're fixed. Okay, so we've got one constraint that you visit each city exactly once. We should also have you leave each city exactly once. So leave each city exactly once. So this is probably now going to be for all I, right? And then we would have a sum over t, a sum over j of x, t, I, j equals 1. So every city will leave once. And now you notice what's going on. The start and the end are actually playing great roles. We leave them once, we enter them once. Yes?
Are we about to write a constraint to make it so you have to visit one city and leave the same city?
I'm sorry? Yes. Now we need to add that constraint. So right now what we have is you have to visit each city once and only once. You have to leave each city once and only once. But maybe we could do some kind of strange thing like this. I go from here to here, then I go from here to here, then I go from here to here. Now I'm here. Now maybe I go here. So let's see. This one has already had somebody leaving it, right? This one hasn't had anybody leaving it, so I go here. And then this one needs somebody leaving it. Go back to them. So let's add 2 more. So now I'll go here, and then I'll go here. That would satisfy the constraints of each city is visited once, each city is left once. But that is not a valid path. So now we need to add the constraint that if you've entered a city at time t, then you leave it at time t plus 1. So if enter at time t, then leave at time t plus 1. So what should be the range of t? 0 to n minus 1. Why don't we go all the way up to n? Why don't we go all the way up to n? I'm sorry?
There is no
there's
time.
There's no time n plus on 1. Our largest time is time n. So eventually we're going to have to add a constraint that we go from city end to city start at time n. And then we'll have to add that at time 0. We'll figure out what that is in a second. So right now we want, if we enter at time t, so what does that mean to enter at time t?
We can do this if now because of last class?
Because of last class, we can write it as if. And I'm not going to expand out if and introduce additional variables. I'm going to just program at a high level.
So if xtij equals 1.
And now what this means is if at time t we travel from city I to city j.
X t plus 1 j I j plus 1.
Yeah.
Well, j plus 1 is a specific city.
Oh,
Because I go from York to New York.
from like any other city
Okay, so we'll call it L.
equals 1.
So this is close. What this is saying is if we travel to j from I, so
Can we say
well,
specifically?
wait just one second. So we start up here at I, we travel to city j, and now we're traveling to city L. Yes.
Can we say that if xtij equals 1, then the summation for all L
Okay.
xt plus 1j equals 1? And that's like an improvement of our leave each city exactly the constraint.
Okay, good. So we don't care where we go.
Couldn't we also even do it for? No, we've already used variable I so now.
Right. We could use I again, but it's better to use a different index here. Now, do we want to put any constraints on L? I mean, if we wanted to, we could say, if we wanted to, L not equal to I or J. I'm sorry, not equal to J. If you wanted to. Because you can't return to the city you started.
Those already have that.
We do. But I'm just saying, when we're doing this sum here, we don't have to sum over all L. We can actually remove 1. Whether or not it's actually worth doing that is another story. Because what we're removing is already forced to be 0. All right, so now what this is telling us is when we look at all possible L's other than J, so we're saying it goes somewhere into L space. Yes?
How does this account for the fact that we don't want to return to some of our expenses?
Because we leave each city exactly once.
We leave each city exactly once. And then if
Okay, so we can't go
so,
back, yeah.
right. But now the other thing is this part correct? So we're basically trying to say, if we're at city J, then we have to leave.
Have to say the summation of overall I.
Yeah, I think we should have a summation over all I. And if you wanted to, you could even do I not equal to J if you want. If I'm at city J at time t, I had to get there. Right? So if I'm at city J, how did I get there? I must have come from some city. Now, which cities will that not necessarily work for? Yes, we've got to be a little bit careful maybe about the start and the end and just think about how we want to put that stuff in. But let's just see, if we assume that the time is at least 1, we're okay. Right?
Should we have some constraint?
So-
summing over all t, it says the sum of I, sum of j, x, t, I, j equals 1. Say that we're only ever leaving one city at a given time. I don't think we have that constraint represented on the board yet.
Let's check and see what this one does right now for all times from 1 to n minus 1. Yes.
Can you explain why we need the sum and the sign?
Well, what I want to do is I want to say, if I'm at city J at time t, then I have to leave city J at time t plus 1.
It doesn't matter which of the x, like that the whole sum of x, t, I, j on the left is equal to 1, or that just...
Well, if this whole sum equals 1, since these numbers are all 0 or 1, exactly one of them is 1. So if I got to city J, there must have been some city I that brought me to J. I don't know which one. So what this is saying is, if at time t I'm at J, then at time t plus 1 I leave J. we don't know how we got to J unless the time is 0. If the time is 0, we definitely know how we got there. Right? And then over here now we've left. So what this is saying is that if at time t we enter city J, then at time t plus 1 we leave city J. And we can't leave it to itself, we have to leave it to something new. We should probably add some constraints about the start and the end. So this is going to affect time 0. So we leave start at time 0. So what that means is the sum over all of j of x, 0, and then start, we're writing it as 0, j equals 1. So this means at time 0, we have left the start. And then leave end for start at time n. So then that would be the sum over
leave n for start, right? Isn't that just x?
Oh, actually, yeah.
X n.
Right.
N plus 1, 0 equals 0. That's a definite.
Right, exactly. I mean, that's an easy way of doing it. We can just say x at time n, we leave city n plus 1 for city 0.
If you match the previous constraint, it would say
right.
Leave a city for the end at time n minus 1. Right?
Right, I think we need to put that in as well.
Okay.
And so this is saying we're leaving start at time 0. This is leaving the end for the start at time n. But you're right, we also need to enter end at time n minus 1. So I'll write the next constraint over here. Leave for end at time n. And this would be
n minus 1.
at time n minus 1? Yes.
Yeah.
Yes. And then at time n we leave end for start.
Wait, but we have n plus 2 cities now. Because we had 1 to n.
Right.
And then we added 2 more. So
let's check.
So we leave start at time 0.
So let's say n equals 3, so we have 3 cities.
So
1,
if we
2,
start
3.
at time 0, then we leave. That means we're leaving. And say we go in order.
Okay.
Then we
So at
leave
time
city
so at
X
time
number.
0 we go to 1, and then at time 1 we go to city 2. At time 2 we go to city 3, and then at time 3 we go to n.
So we leave the n for the start at time n plus 1, which means we leave for the end.
At time n.
Yeah.
So we've got 3 cities.
Right. Yeah.
We add the extra city 0. Let's do it this way. So we have city 0. We have cities 1, 2, and 3, and here's our city 4. So at time 0 we travel to 1. At time 1 we travel to 2. At time 2 we travel to 3. At time 3 we travel to 4. And then at time 4 we travel back to 0. So if we had 3 cities, we have 4 times. So our time here should go up to n plus 1. Yes?
I'm not exactly sure about it, but isn't there some way, since we've already guaranteed that at the end we'll return to start, and at time n minus 1 we'll, like, we can only leave and visit each city once already, so there's only one place to go.
Right, so
Like,
what you're saying is these 2 constraints might actually force us to travel to end at time. I think you're right.
And those with the if then.
Right. Because we leave start at time 0. We return to start at, no, this should be, I think, time n plus 1.
Yes.
Okay. we return to start at time n plus 1 from city n plus 1. So if we have this constraint, the only way that could work is if we entered city n at that time. So I don't think we need it. If we wanted to write it down, how would we write down we leave for end at time n? It would be the sum over time n over city I n plus 1, summing over all I, that would equal 1. But probably do not need. So the question is, will it actually help the algorithm? Will it help the program if we put in this additional constraint? Or would the program take more time because it has to go through the logic and realize that it has to go to city n plus 1 at time n? And this comes down to runtimes of which I honestly do not know. If you want, I think it would be outstanding to write a simple program to do this. I am not going to require it for this class, but I strongly encourage you to write a linear programming problem to do this. Mathematica allows you to do linear programming. How many cities should you do? 1,000? You can do linear programming in Mathematica. You can do, I think, linear programming in R. There's lots of different environments out there that do linear programming. I strongly urge you to do this. This is not a computer science class. It's not co-listed with computer science. I'm not going to make you do something like that. But it would be really good for you to be able to say, after taking the course with a huge theme on linear programming, that you actually wrote a linear programming problem. Do you think, for the purposes of learning how to do things, you should do 1,000 cities? How many cities? 10, 5, 4. You know, the point is to actually just be able to write down the program. You want to get the skill. And then what you could do is, if it's modest-sized, you could see, does it actually run faster with the constraint or not? How do you input the constraints? There are ways to just generate these. I don't think this is needed. I think you're absolutely right. And remember to email me for the notebook that this is redundant, that the other stuff forces it. It is quite likely that somewhere in here we've mixed up an index. Or maybe we've forgotten to do something with the start or the end. So the good thing to do now is, after we've done this, is to write all the constraints clearly, boom, 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 really think about it. What I want you to get from this is that we can solve problems like this with integer programming. Unfortunately, the runtime is terrible. But if you are doing a trip that's in the tens of thousands of miles, do you care if you're off by half a mile for the optimal route? No. You're going to eat up more than that just going off the highway sometimes to hit the restroom or to go pick up food. So we can get very close to the optimal very quickly. If anybody's interested, I know somebody had just claimed this chapter earlier this morning. I have a really nice book on the traveling salesman problem, which talks about applications and talks about attempts to get to the solution. And then what we'll do, if people are interested in the next class, there's a couple of other approaches you can do. There's the insertion algorithm, there's the subproblem. If people want me to do those, I'm happy to talk about them. Just shoot me an email. It's a question of how much linear program do you want to do. I want to just end the day with doing a simpler example. But first, any questions on this? This is not that bad to write down as a linear programming problem. The difficulty is then solving the binary integer linear programming problem. But if you have a black box, and there are plenty on the market, IBM has a really nice one which I've had students use in the past. It will solve these things fairly quickly. Or if not solve them, at least get a really good close approximation. So at some point there will be a midterm. You will almost surely have a problem where you have to do a linear programming. It'll be a theoretical one where you'll have to write down the constraints. Okay? And it's going to be something like this. Choose your variables. Choose your constraints. If you want to put in a few extra constraints, by all means do so. So long as they're not wrong. If it's just, I want to code all these things. I'm not trying to find the most elegant, simplest set. If this is redundant, I don't care. It's not harmful to have it. That's all I care about. How many of you have ever played the game Battleship? How many of you have ever played Battleship by yourself? Well, we're talking about visiting yourself. So maybe you decide to have a play date with yourself. Although my son is now old enough that he says, Dad, it's not a play date, we're hanging out. Yes. So let's say you decide to hang out with yourself to play Battleship. Would you play the standard game of Battleship? Why not? You really can't play the standard game of Battleship. Gee, I wonder where I hid my carrier. Oh, what a surprise, I got it. Have you ever played one-person Battleship? So the way one-person Battleship works is the following. 1, 2, 3, 4, 1, 2, 3. You have, say, an n by n board. And I give you a collection of ships. 1 by n1, 1 by n2, dot, 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 1 by nk. And the ships are placed on the board. And for those of you who are taking probability or have done some statistics, I'm going to basically give you the marginals. I'm going to tell you, and again, ships can only be placed horizontally or vertically. You're not going to have a ship moving diagonally. This is just an intro class in operations research, okay? And the ships are all straight line segments, okay? All right? I'm going to tell you how many ship units are in each row. Okay? So maybe there's R1 in the first, R2 in the second, Rn in the last. And I'll tell you how many column units of ships there are in each column. C1, C2, Cn. So Ri is number of ship units in row I, Ci is number of ship units in column I. What's the goal?
Oh, this is like a logic problem.
Yeah, it's like a logic problem.
Actually, this is a logic problem.
Yes.
This is very
If the camera weren't rolling, I could talk to you about logic problems and legal decisions. All right, so this is a logic problem. Can you solve this with integer programming? Probably, given that this is an integer programming class and I'm talking about it.
Yeah.
Do you think that the solution is unique?
Yes.
In probability, if I give you the marginals, is there a unique distribution that has those marginals? Or can you have different distributions? Yeah, so in probability, just because I've given you the marginals does not mean I've given you the distribution. So as a nice exercise, come up with a situation where I give you the marginals.
We're given like two endpoints of shift, right? It might become unique.
Well, the other thing is, what do you want to consider unique? So here's a stupid non-uniqueness. I have two destroyers, a sub and a cruiser. I could also flip the order of the of the destroyers and the sub cruisers. Instead of going 2, 3, 2, 3, I could go 3, 2, 3, 2. Would you consider that distinct? It is. I could also go 2, 3, 2. What conditions do you need on the ship lengths to ensure that this does not happen? So that's almost really a difficult problem.
Sorry, that what doesn't happen in configuration?
That you don't have two different configurations that have the same marginals.
You need non-adjacency. Otherwise, you have like a 2, 3, and a 5. And you get that like 2 by 5 block.
So if two of them sum to a third, we're in trouble. Or if two of them sum to another 2, we're in trouble. Oh God, this could get really bad. Right now, this is a really nice problem in number theory. But of course, this is only trying to avoid certain types of configurations like this. So I could do maybe a 2, 3, and I could have a carrier which is 5. Yes?
So what if you just had 2, 3, and then just flip them, so it's 3, 2?
Right. And so would you consider that different? Or would you want to say, come on, it's the destroyer is, come on. So you have to decide, do you really consider that different or not? To me, if I flip these, it's different, but it doesn't feel as different as this. And so in some sense, we could put an additional constraint. If you ever have two ships in a row, or two ships in a column, and they're adjacent, then the smaller one comes first. This is like when we have primes, we have every number is uniquely written as a product of prime powers. Because we now assume that we have to write it as increasing primes, so that there's now a unique ordering. If we put in something like that, we can try to put some things that would eliminate these flips, but it would not eliminate a configuration like this. This would be fundamentally different. So this becomes a nice, interesting number theory problem. If anybody's taking number theory next semester, I'm happy to consider studying that next semester. We would need to write down constraints for this. What do you think the constraint should be? What do you think the decision variable should be? Let's see how much time we have left. So we have about 2.5 minutes. What do you think our constraint should be? What do you think our variable should be? There's a couple, I can think of at least 2 ways to do variables.
You'll see whether there's a ship unit in IJ.
Just any ship unit? So one possibility is I could check and see, does it have a ship unit from ship 1? Does it have a ship unit from ship 2? Does it have a ship unit from ship 3? And then I could have constraints, which would say, if I have a ship unit of ship 1, I have to have a consecutive swath. And you have to think, what's the best way to code that? That's one way to do this. I think there's a better way of doing the problem. I think we should do this like it's movies. Yes?
So in this version of the game, though, when you get a hit, you know what ship it's from?
Well, you're not actually getting a hit. Your job is to go, is to reverse engineer and get the distribution of the fleet based on this information. So we have some Boston spies who gave their lives to give us these strings of numbers. But it may be a trap, yes.
Just like you said, you just have variables for the start of each.
Yeah, I would do it variables for the start of each ship. And I would have 2 types of variables. The x's would be, so say x, I, J, S would be, we horizontally in row I, column J, start ship S. And I would have Y, I, J, S, B. We vertically start in row I, column J, ship S. I think those are much better decision variables. And then you would just fill down.
Do you also need parameters for the lengths of the ships?
Yes, but we know what the length. Ship 1 is at 1 unit, ship 2 is at 2 units. So I tell you the length of the different ships. And so what you would then say is that if I start a horizontal ship of 2 units here, the ship is going to now look like this. I can't start another horizontal ship here. I can't start a vertical one here. I can't have a vertical one here coming down into there. And you'd have to find a way to code all of this. So it's a really nice exercise. If you want to practice your linear programming, write down how you would write the linear programming for this problem. Okay. This is a good place to stop.